100 years, the industrialized world has been burning fossil fuels. Coal, oil and gas are the buried remains of ecosystems laid down millions of years ago. Now they have been unearthed and are being put to work in everything from steam engines to jet aircraft. They power the lifestyles that many of us take for granted. The Earth's temperature is finely regulated by naturally occurring gases in the atmosphere. Their presence keeps the surface of the planet warm enough to sustain life. Burning fossil fuel produces gases, including carbon dioxide, which are enhancing this natural greenhouse effect. In the year 1000 AD, carbon dioxide was present in the atmosphere at about 270 parts per million. Around 1800, human combustion of fossil fuels began to leave an imprint on the atmosphere. Rapidly industrializing societies were suddenly releasing more carbon dioxide than the Earth's ecosystems could absorb. It took another 150 years for science to recognize the consequences. After decades of debate and denial, the picture is now clear. We, in the industrialized nations, are changing the climate. Every year, carbon building up in the air is trapping more heat close to the surface of the planet. On a large scale, this is influencing global weather patterns and ocean currents. No one knows what will happen next. The Greenland and Antarctic ice caps have begun to melt, putting coastal settlements under threat of catastrophic flooding. Weather patterns are less predictable, and extreme events such as hurricanes and cyclones are occurring more frequently and with increasing power. Whole ecosystems are on the move. We are threatened with mass extinction of species that can't keep up with their changing environment. Human society and agriculture is predominantly coastal. If the sea invades these heavily populated areas, hundreds of millions of climate refugees will be displaced. If we let this happen, there really will be no going back. There is still time to prevent this climate catastrophe, but we need to cut our greenhouse emissions to less than 20% of present levels. This means phasing out fossil fuels. The countries which are polluting the most need to make the biggest changes. And it needs to happen soon. Before we can cut back our carbon emissions, we need to know where the pollution is coming from. The biggest single source of greenhouse gas emissions comes from burning fossil fuels for electricity. Agriculture, transport and waste are also significant contributors. Some of the fuels we burn have higher greenhouse emissions than others. Coal is the most greenhouse intensive of all, even with improvements in efficiency. Gas is much more greenhouse efficient than coal, but it's still a non-renewable fossil fuel. Ideally, we would switch to renewable energy sources like wind and solar, which produce almost no carbon emissions. But these sources are said to be unreliable and too small-scale to cope with our massive demand for energy. To make the situation even more difficult, the world is rapidly approaching the peak of oil and gas extraction, which is forcing prices up and making the search for alternatives much more urgent. For business as usual to continue, we need a large, centralized source of cheap, safe and reliable energy that produces no greenhouse gas emissions. This is the Cattenom nuclear power station in France. Its 4 reactors generate enough electricity to power the entire southwest of Western Australia. Its carbon emissions when operating, 0. "100 years ago, an obscure patents clerk in Switzerland realized that the atoms making up ordinary matter were themselves composed of enormous amounts of pure energy. Early 20th century machines were not capable of breaking atoms apart to release this energy, but it was only a matter of time before technology caught up with Einstein's theory. The key element, when refined to extreme purity, is a metal known as uranium. This is one of the few naturally occurring elements on Earth that is radioactive. That means it is unstable and prone to collapse, releasing some of its energy as radiation and tiny atomic fragments. As it does so, the uranium is transformed into a different radioactive element, which in turn decays over time through many transformations until eventually a stable form of lead is reached. If uranium is enriched to a high enough purity, these tiny disintegrations can be engineered to set off a chain reaction, with each decay setting off more atomic collisions. In the dark years of the Second World War, the major powers raced to turn these invisible atomic reactions into a weapon. In August 1945, the United States destroyed Hiroshima and Nagasaki with atomic bombs. The war was over, and the nuclear age had begun. The military reactors which produced the weapons-grade material also generated vast amounts of heat as a byproduct. By the late 1950s, these wartime models had been modified to drive steam turbines for electricity. First redesigned on a small scale for nuclear warships, these reactors were then scaled up, and the world's first commercial nuclear power stations went online. As other countries scrambled to develop their own nuclear weapons, the technology spread around the world. A new era of peaceful nuclear energy was heralded. From these beginnings, the commercial nuclear industry grew rapidly in a handful of countries until the 1980s. By 2005, 441 commercial nuclear reactors accounted for around 16% of world electricity generation and 6% of total commercial energy. Most of the remainder is generated by the carbon-intensive fossil fuels that are heating up the planet. To extract such vast quantities of energy from such an unconventional fuel, the nuclear states have built an industrial complex that spans the globe. This fuel chain begins with uranium mining. In a conventional mine, uranium-bearing rock is dug up from open-cut pits or underground tunnels. It's trucked to uranium mills where it is crushed to a fine powder and chemically treated to separate the traces of uranium. To produce 1 ton of uranium oxide, or yellow cake, around 660 tons of rock is crushed and discarded. To fuel a conventional nuclear power station for 1 year, 200 tons of uranium are needed, leaving behind 130,000 tons of waste. This radioactive waste rock, or tailings, is dumped next to the mine in huge dams. It contains a cocktail of radioactive decay products and needs to be isolated from the environment for tens of thousands of years. Uranium mining is highly water intensive. The Olympic Dam mine in South Australia consumes 33,000 tonnes of water a day, making it one of the largest water users in the country. The uranium is then transported to enrichment plants, where it's converted into a gas and purified further. The 200 tonnes of uranium oxide yields 24 tonnes of low-enriched uranium suitable for nuclear fuel. Enriching the uranium further yields weapons-grade material, making enrichment plants a key technology for nuclear weapons proliferation. One waste product from the enrichment process is so-called depleted uranium, or DU.
Copy 6 miles. Let me know when you see the target area and I'll start the talk on.
We see it, start talking.
We're there, start talking.
Hundreds of tons of DU have been machined into ammunition and fired into Kuwait, Bosnia, Iraq, and Afghanistan. Radioactive dust from these munitions has already caused sharp rises in cancer and other illnesses amongst military forces and civilians alike.
Flares. Okay. Continue engage.
The enriched uranium is transported to fuel fabrication plants and carefully manufactured into nuclear fuel assemblies. These are loaded into the nuclear power station, where the intense heat of the nuclear reactions in the fuel is used to produce steam, driving conventional turbines to generate electricity. The extreme heat, pressure, and radiation fields in a nuclear reactor demand precision engineering and constant vigilance by plant operators. After more than a year in the reactor core, the fuel becomes too contaminated to sustain a chain reaction. The irradiated fuel assemblies are set aside in pools for several years until they are cool enough to be transferred to sealed sheds next door to the reactors. Spent nuclear fuel is so intensely radioactive that all handling must be done by remote control. It needs to be isolated from people and the environment for hundreds of thousands of years. As yet, it is not clear whether it will be possible to achieve this. One proposal is to encase the fuel in lead, steel, and copper canisters before burying them in stable geological formations deep underground and backfilling the tunnels with remote piloted vehicles. But in time, the waste will escape even this containment. After 60 years, there's still no foreseeable solution to the nuclear waste problem. A small number of countries operate reprocessing plants to extract the exotic element plutonium, which forms in the spent fuel. In theory, this is done to provide fuel for a new generation of plutonium breeder reactors, which create or breed more plutonium than they burn up. In practice, after several accidents and more than $100 billion in funding, no one has ever been able to build a commercially successful plutonium reactor. For this reason, there are now more than 270 tons of separated plutonium sitting in civilian stockpiles around the world. It takes as little as 4 kilograms of this material to make a bomb capable of destroying a city. nuclear expansion will radically increase the amount of nuclear materials in circulation. At the same time, the system of international safeguards intended to restrict the availability of nuclear weapons is breaking down. In the past decade, the International Atomic Energy Agency reported more than 650 cases of smuggling involving nuclear and radioactive materials. Until the existing nuclear weapon states finally dismantle their Cold War stockpiles, every ton of uranium mined adds to the risk that one day these weapons will be used again. When power stations and reprocessing plants are no longer safe to operate, they are shut down and left to cool for several decades. Eventually, they will have to be carefully dismantled and buried. In the UK alone, the clean-up bill for a number of civil and military nuclear facilities is estimated at more than £90 billion. Every stage of the nuclear fuel chain produces radioactive materials. Radiation affects our bodies in different ways, depending on the kind of radiation and whether the dose is internal or external. It is possible to shield against external sources of low-energy alpha or beta radiation. But if inhaled as dust or swallowed with food, these radiation-emitting particles can lodge in our lungs and other organs. Once embedded in our bodies, radioactive chemicals bombard nearby cells at close range with enough energy to rupture cells and damage DNA. Internal exposures are particularly dangerous, as some radioactive isotopes accumulate in specific parts of the body. This in turn can lead to cancers, organ failure, and a host of poorly understood diseases which can show up years after radiation exposure.
I am advising pregnant women and preschool-aged children to leave the area within a 5-mile radius of the 3 Mile Island facility until further notice.
Controlled release of radiation from the 3 Mile
Please
Island.
remain indoors, doors shut, windows shut, fans not operating until you hear word that it is safe to go outside.
In March 1979, Unit 2 of the 3 Mile Island reactor in Pennsylvania suffered a loss of coolant accident and melted down. For several days, plant operators fought to keep the reactor core from exploding. To avoid such a catastrophe, operators released several hundred tons of radioactive gas into the air and eventually brought the power station back from the brink. No nuclear plants have been ordered and built in the United States since then. In April 1986, the Chernobyl nuclear power station in the Ukraine exploded following an engineering test. Thousands of soldiers and workers sustained massive radiation doses in an attempt to quench the molten fuel and contain the disaster. The radiation plume spread around the world. 350,000 people in surrounding areas were evacuated and can never go back. Sharp increases in cancer rates and child mortality across the region were the most immediate consequence. Altogether, more than 5.5 million people still live in contaminated zones. The nuclear industry has tried hard to downplay the Chernobyl accident as a one-of-a-kind. But in August 2006, plant operators came within half an hour of another meltdown at the Forsmark reactor in Sweden. There have been other near misses in India, Germany, and the United States. Despite this extraordinary history, some people still suggest that nuclear power has a role to play in the urgent transition away from fossil fuels. Australia holds around 30% of world uranium supplies. We're the world's second largest uranium exporter. In 2005, we sent 9,500 tons overseas. Spurred on by industry speculation and a supply shortfall, the world uranium price has begun to rise. Australian politicians are being encouraged by the mining industry to cash in on expanded uranium exports, starting with the Honeymoon mine in South Australia. A major exploration boom is underway, identifying prospective uranium mines right across the country. An aggressive push has begun to build enrichment plants and up to 25 nuclear power stations in Australia.
And we're going to use new technologies that effectively and safely recycle spent nuclear fuel. In other words, we're coming together to say, how can we do a better job of reprocessing and recycling fuel?
And under the United States Global Nuclear Energy Partnership, Australia is again being promoted as an ideal location for dumping the world's high-level nuclear waste. It is argued that this is the price we must pay to maintain our current levels of energy demand in an age of climate change. Unfortunately for the nuclear industry, there is one last catch. Every stage of the nuclear fuel chain is heavily dependent on cheap fossil fuels. With every passing year, high-grade uranium deposits are being depleted. As more reactors are built and ore grades decline, more and more energy has to go into producing nuclear fuel to get the same energy out. In a few decades' time, nearly 2 million tons of rock will have to be crushed, chemically treated, and left in enormous tailings dams to power one reactor for 1 year. Adding this to the enormous carbon emissions of enrichment plants and other stages of the nuclear fuel chain, we find that in time, nuclear plants will generate as much greenhouse pollution as gas-fired power stations. There is no way that nuclear power can claim to be a solution to climate change. Many are now looking elsewhere for answers to the climate crisis, and fortunately, those answers are all around us. A range of renewable energy technologies are taking off. Intermittent sources, including solar and wind, are being combined with baseload sources, including geothermal, biomass, microhydro, and combined heat and power systems. In countries where institutional and market barriers to these new technologies have broken down, uptake of renewable energy has been spectacular. Many nations and states are adopting ambitious renewable energy targets. China has established a 15% target by 2020, and California has adopted 20% by 2017. Other countries are aiming much higher. Australia still has no renewable energy target. Green energy sources are combining with new ways of thinking about energy. Using energy more efficiently means we end up using less, and it's much cheaper to save electricity than to produce it. We are being offered a false choice between climate change and a radioactive future. But there are no technological barriers to a world powered by clean energy. The barriers are entirely political